Benjamin could start recording if he's not already.
We're recording.
Fantastic. So welcome everyone to this second seminar in our series. This series is called Future Leaders in Mechanical and Aerospace Engineering, Celebrating Diversity and Innovation. And this is really a United States national-wide event that we are doing this year, this academic year, and hopefully beyond, to highlight the contributions of PhD students and postdocs who are doing fantastic work in the fields of mechanical and aerospace engineering, and also are representing groups who we sorely need to diversify the professoriate. And so we're aiming to encourage students, we're aiming to help give them feedback. There is a mentoring session associated with each one of these events. And I want to thank the co-organizers of this series, including Samuel Graham, John DeBeery, and Howard Stone, as well as our fantastic population of advisors for the series, as well as those of you who have volunteered as mentors. So we're going to get started today. As with every seminar, we feature two speakers, and I will be asking either I will introduce or an advisor or mentor of the speaker will introduce. And let's get started with our first speaker. So our first speaker today is Matthew Clark, and I'm pleased to introduce him. His research is focused, he's a PhD student at Stanford University in the Aeroastro department, and his research is focused on the development of tools to design, analyze, and optimize electric aircraft for urban air mobility. And he'll be, I'm sure, telling us a lot more about that. So I'd also like to mention that he's done an amazing job in terms of involvement in university-wide initiatives at Stanford, including URM, graduate recruitment, and student organizations that really show his commitment to fostering diversity and inclusion in our graduate student community and beyond. So we're really excited to hear about your work, Matthew, and I'm going to play a little chime about 3 minutes before the end of your talk, your 20 minutes, to let you know when it's time to wrap up. So I will hand it over to Matthew to go ahead and share his screen.
Thank you very much, Alison. Let me share my screen. Can everyone see my screen?
Yes, we can.
Yes.
Perfect. Thank you. So once again, thank you, Alison, for the introduction. It's truly a pleasure. It's truly a pleasure to be here today, not only to talk about my research and engage with some of the brightest minds in the future in the realms of aerospace and mechanical engineering, but also to celebrate diversity in academia. Today, I'll be talking about the prediction of the operational envelope of electric aircraft through robust battery cycle life modeling. And that is a mouthful. So like most titles, I'm going to break it down before I even go any further. So when I talk about the operational envelope of electric aircraft, I'm simply referring to the flight profile. While the aircraft actually flies throughout the mission from one airport to the next. That includes a climb, cruise, descent, and reverse thrust, etc. However, over the past few years, there has been a sort of a disconnect between aircraft designers and actual the performance of the aircraft. And I think that area is due to the lack of modeling in terms of the battery network system. So this presentation is particularly focused on that. So I will first start with an overview, then I will go into battery modeling in aerospace applications. I'm going to then talk about the flight profile simulations that I ran, some preliminary results, and then end with a conclusion. Because this talk is only about 20 minutes, I'm not going to go into the heavy math of the problems I'm solving. I really want to spend this time actually just stressing the importance of battery modeling. As Alison said, my work is actually revolves around the aerodynamics and aeroacoustics. However, in modeling these vehicles over the past years, I realized there is a disconnect, and I wanted to solve that issue. So to do that, I actually took inspiration from the NASA X-57 aircraft Maxwell, which is an experimental aircraft designed by NASA essentially to spearhead the certification of new electric aircraft and stuff like thermal runaway. How do you actually model one engine in operative situations, etc. So this aircraft is that this presentation is actually going to be focused on that aircraft. Moving on. So, like I said, before we actually go into any of the mechanics of this presentation, I want to first step back and actually talk about batteries. And this is actually a learning process for me over the past year, and I'm hoping to actually share some of that knowledge with you today. So a battery is essentially an electrolytic cell made up of a few components. Typically, there's a current collector, there's a positive electrode, which is usually a metal oxide, a separator electrolyte, which is usually a solvent or organic solvent, and then the anode, which is typically graphite connected to another current collector. Now, typically, batteries are actually distinguished by what is the lithium metal at the cathode. And as you can see in the spider chart to the right, we have different lithium metal chemistries. For example, if you look at the third one, lithium iron phosphate, we can see here that this chemistry actually has a great lifespan. However, it has a very low specific energy and specific power density. And that means that this battery is essentially pretty large and bulky compared to other batteries. And that is why this battery is typically used for electric buses. Compared to batteries such as the lithium, nickel, cobalt, aluminum oxide, this guy here, as well as the lithium, nickel, manganese, cobalt oxide batteries, these batteries have high specific energy and power densities and are therefore typically used in aerospace applications. In this presentation, I'll be particularly focusing on these two batteries. So how does a battery work? Well, essentially, when you charge, in charging, there is a simultaneous movement of lithium ions from the positive electrode to the cathode. Movement of ions, from the positive electrode to the negative electrode through the battery cell, simultaneously occurring with the movement of electrons outside of the battery. Now, what you typically see, however, is a discharging phase where, similarly, electrons move from the negative electrode out of the circuit through to the other side of the current collector. At the same time, lithium ions move from the negative electrode to the positive electrode. So before I actually talk about batteries, you can get an understanding that because of the movement of lithium ions and electrons through the electrodes and the electrolytes, you're going to have a lot of mechanical stresses being created. You're going to have a lot of exfoliation, etc. And this is what actually causes the batteries to break down. So when an aircraft designer creates a battery, he actually needs to actually take into consideration how is the battery going to perform at its 100th cycle, at its 300th cycle, or 365th cycle, in other words, a particular year. Now, what exactly did that structure that I just showed you, how does it relate to a battery? Well, if you take your AA batteries, your 18650 batteries, those are essentially just this structure here, formed in a jelly roll structure and contained in a casing. So that's essentially what a battery is. In this particular study, I'll be looking at cylindrical cells. However, for aerospace applications, there's also pouch cells which don't have the protective casings. Therefore, they're a little bit more bulkier because you have to actually have a protective layer to protect your battery cell. So, like I just mentioned before, my goal for this research is essentially addressing the shortcomings in battery modeling at the conceptual design stage. And I've showed you before, there has been little emphasis placed on quantifying the battery state of health. I talked about the stress factors, which can be enhanced by repeated cycling, thermal stresses due to internal resistance and heat dissipation, the growth of the solid electrolyte interface. So if you remember correctly, or I'll show you again, as the lithium ions move from the negative electrode to the electrolyte, there's also a buildup of a byproduct on this interface. You can imagine this byproduct actually reduces the size of these gaps and reduces the capability of lithium ions to actually attract to the electrode, hence reducing the energy capacity of the battery. As well as exfoliation, which occurs as the lithium ions form or remove themselves from the structures of the electrodes. All these factors actually influence the energy storage capacity of the battery. So here are my research objectives. The first one is just to outline the implementation of a discharge and aging model for lithium ion batteries. The second is which is most important, to predict the cycle life of an electric aircraft with a particular mission. And I want to stress particular mission because each discharge cycle and each aging cycle is going to be affected by the type of mission flown. For example, if you have an eVTOL mission that has very power intensive climb and descent segments because they're vertical, you're going to have a different discharge profile. And the last thing I'm going to do, and in this presentation, I'm only going to talk about one of the sensitivities, however, is just to identify the batteries, the sensitivity of battery chemistry, rates of climb and descent, as well as range on the discharge rate, cycle life, and state of health. So I'm going to look specifically at how your aircraft mission actually impacts on the battery degradation. So the first things first, we have to look at the model we're using. And this model comprises of three parts. It has a cell discharge model, a thermal model, and an aging model. So let's first start with the discharge model. For this model, I use the Thevenin base circuit, which is capable of characterizing key properties of the discharge, such as the transient state, which is essentially the state as soon as the battery discharges and is not yet fully to the steady state level. Those areas are very important, and particularly during high frequency modulation, for example, when the aircraft is actually flying and the loads are changing. This model, the reason why I also use this model is because it was adaptable for different cell chemistries. So as I told you before, in aerospace applications, we typically use the NMC chemistry, which is the lithium, nickel, manganese, cobalt oxide, or the NCA chemistry, which is the aluminum oxide chemistry. So this model, to get the experimental parameters, we basically use experimental tests. We do a little bit of parameter fitting, and then we apply it to a discharge circuit. For the thermal model, however, the temperature and heat generation is determined through the conservation of energy and the Gibbs function using a relation first proposed by Bernardi. And the reason I use this as opposed to typical HA delta T models or thermal models is because I really want to get an idea of how the airflow throughout your cells can impact on the cell aging. So here we have a battery module, which can be represented as a series of cooling fins. These cooling fins, or cooling tubes, these cooling tubes have air flowing through it. And from there, you can determine the appropriate Reynolds number, then the appropriate Nusselt number, and use that to actually determine the convective heat transfer out of your battery cell. And with this, you can actually build up from fundamental principles the thermal distribution within the cell, as well as within the battery pack. Last but not least is the degradation model, and this model was taken by Small-Stegan, and it actually characterizes the aging of NMC cells. These cells can be categorized, this aging can be divided into two. There's calendar aging and there's cycle aging. The calendar aging is the time, and cycle aging is the repeated number of cycles. And here we have expressions for, I'll put in another equation later, for the the calendar and the cycle aging. Combining these equations, you can produce what I call the capacity fade. Sorry, that's supposed to be model, as well as the resistance growth model. Like I mentioned before, both the capacity decreases, but also the internal resistance increases, and these functions are given. These functions are given as a function of time in days. So looking at the X57 model, the Maxwell, sorry, I simulated this in a simple flight profile with a constant ascent rate, constant speed, and constant descent rate, as well as charging time in the ground segment. So I just did a simple segment flying for a simulated time of 4 times per day for an entire year. And here we see the breakdown of the mission, where we have the climb segment, cruise segment, the descent segment, and the battery energy increases back to gain to full. Now, this is a very simplified model. I actually do have models that have different segments depending on the actual FAA regulations, which includes the initial climb above a certain height. Then you have your approach procedures, baseline, etc. But I just want to give you an idea of the type of modeling being done. And this aircraft flight profile is actually connected to the temperature within the battery. So you can imagine as the aircraft climbs and the power is at max throttle, you have a very high increase in temperature. And as the aircraft cruises and descends, the battery temperature actually reduces. However, when you charge again, the battery temperature is going to once again rise. And here I have here the battery voltage and the C rate plotted as well. Interesting to note as well is that when the battery state of charge is extremely low, the C rate is particularly high. Why is that the case? Well, your motors need to be the motors require a certain amount of power, which is current times voltage. At a low states of charge, your voltage is pretty low, so your current has to be pretty high. If you remember from the equation showed you before, those equations actually depend on current. Therefore, you're going to have a lot of aging during that phase of flight, or a lot of degradation. Sorry. So to get an idea, to get a real engineering feeling of what I just talked about, I actually just modeled this flight, simulated in a model flight from San Francisco with an initial range of Sacramento. Now you can see from the plot to the right that after an entire year, that aircraft does not actually meet that mission. And that's what we see here also to the left, where we see the capacity fade in the battery actually decreases by about 15%, as well as the internal resistance increases. I also plotted here in green the capacity, the daily temperature, because these models require, these models actually are meant for air cooling batteries. And the air is actually the atmospheric air. So as the temperature rises throughout the year, around the late summer, you have, I think this is around 25 degrees Celsius, and it drops. So that temperature is also taken into consideration in your thermal model as well. The only sensitivity study I want to talk about today, which is pretty interesting, is the sensitivity study of the impact of rate of climb on battery life. We see here that to reduce the amount of capacity fade, or the internal resistance growth, actually requires a high climb rate and a small descent rate. Essentially, we want to fly our aircraft at a steep climb rate initially, where the state of charge is high, therefore the current passing through the battery is low, compared to the other way, where if we have a low climb rate, we see that there's more degradation within the battery. And I'm happy to talk about this more in the question and answer period. So in terms of what I've shown you, the batteries I used in this study actually assumed a constant specific heat capacity. As you can imagine from what I told you initially, these batteries are made up of layers and then rolls of electrode, and then current carrying conductors. What in the future I would like to actually remove this assumption of a specific capacity of the entire battery to allow to see the actual changes in temperature of different cells within the battery, and also apply this model to more non-conventional vehicles such as the ones used for urban mobility, such as stop rotor, tilt wing, tilt rotor, and multi-rotor configurations. So what I've shown you today is that robust modeling is a critical component in electric aircraft design. And a lot of people are designing aircrafts with particular energy capacity, but forget to include how that battery is going to look like in tomorrow, or actually 10 days or a year from now. These actually affect the designer's choices and can have very large ramifications on the aircraft design process. And the last thing I will mention is that the mission of these cycle life studies, like I said before, can result in the over prediction of performance, which can lead to an aircraft failing to meet its range requirements. That it concludes my presentation.
Perfect. Thank you so much, Matthew. Great presentation. We can now, yeah, we have a virtual claps, I see from the audience. We can now move on to a Q&A period. And you can put your questions into the chat, which I am monitoring, or you're welcome to also simply unmute in order to ask your question. But let me start by calling on David Go. Why don't you go ahead and unmute David and ask your question?
Matthew, thank you very much. That was a very interesting talk. One of the things, right, that you show is that as the battery degrades, you can't meet the flight profile. And so you can either improve the battery or you can change the flight profile over time to accommodate battery degradation. Have you explored the latter one? I'm actually particularly interested in that. Ways that you can be more intelligent about the flight profile to match where the battery performance is at any given moment in time.
Yes, that's a great question. I have not explored that, but you're precisely correct. We can actually design an aircraft with the intent of first having an intended mission from San Francisco Airport to Sacramento. But if you look at this plot, we see here that there are also airports in Santa Rosa, Oakland, as well as San Jose. So there is the potential to maximize on the utility of these aircraft, given the fact that these batteries will degrade. But I have not actually looked at that specifically in this study. Thank you.
All right, thank you.
So there's a question in the chat from Bert Brass, which is, the question is, are you assuming active or passive ARI cooling?
Well, it means air cooling, sorry, typo.
Oh, air cooling, thank you.
I am assuming active air cooling with a velocity of 0.1 meters per second. That's just the velocity I chose based on studies by Toyota in their battery module studies. However, that number itself can change, and with a change in that number would change the Reynolds number, the Nusselt number, the heat transfer, convective heat transfer coefficient, heat transfer rates out of the battery. So changing that number would definitely change the amount of heat within the actual battery pack.
Great, thanks, Bert. Any follow-up questions, or should we move on?
You can move on, thanks.
Okay, thank you. Howard, you had a question. Feel free to unmute and ask it.
Matthew, that was really wonderful. I think you're in a position to frame an answer in a very beautiful way, but I might be showing my age, which is that in some ways, if you can phrase an answer in terms of axes that are both non-dimensional, then you've answered many people's questions at once. In other words, I don't know what the right variables are, but you know, or you'll figure it out, whether it's relative to the initial energy or power density in the battery to start. But I think if you were able to frame your model or its output in terms of some relevant dimensionless parameters, first of all, we'll then name them after you. But second of all, you'd actually have a universal way to view the questions and answers rather than just everyone having to answer specific questions. And I realize this is less common now that computers are everywhere and people just calculate things. But I really think that you've outlined a framework that you could maybe figure out a way to present it that is really universal in trying to think about some of these things. And I don't know what the answer is, but I bet you could sort it out. And I think it'd be very interesting.
I would love to have a number named after me. I think that would be a bad thing.
About that. But I mean, a framework for representing answers.
Yes, but interestingly enough, if you look at this plot, you see here, I do actually take the capacitance and divide it by the initial state. I guess this is sort of a percentage change, which can be used to represent any particular battery, regardless of what is the initial energy capacity. You can actually calculate the non-dimensional difference in increase or decrease of any parameter you have.
I think if you could do that for your previous graphs, it would be really great.
Yes. Okay. Will do. Thank you.
Welcome.
Thanks. And there's a question in the chat from Amitav Tikadar, which says, for a parameter estimation from your experiment, which tool have you used?
The experimental data I used in this experiment was obtained by studies that I didn't conduct. So I used the experimental data to create these models. The experimental tests were done using pulse precipitation tests, which are essentially, if I go back further, essentially you have a particular battery and you just essentially run it a particular time and measure the change in voltage. Actually, if you can look closely here, the change in voltage at a particular time and how it actually changes over time. And you can use that to create to create the parameters such as the Thevenin resistance, the Thevenin voltage, as well as the Thevenin capacitance. So I didn't actually run the experimental test. I just collected the data, which collecting battery data is actually pretty hard because it's really hard to find. It's very proprietary. And I used that to create these models.
Hey, thanks, Matthew. I think we probably have time for just one more Q&A. So before I call on Tim to unmute to ask his question, I'll just note that Matthew, afterwards, if you like, if voluntarily, you could answer any other questions that show up in the chat. Feel free to just also answer them in the chat since we probably won't have time to get to them. So Tim, why don't you go ahead and ask the last question?
Okay, thank you. A really nice talk, Matthew. I can kind of capture some of the other things in my question, which is, to what extent have you thought about incorporating uncertainty quantification? I think we all know that the performance of a battery, of any given battery, is quite variable. And it seems to me that your model is ripe for including some kind of statistical analysis. What have you thought about that?
I think that's a good approach. I think that's definitely the next step. And the reason why I agree with you is because even within a battery, let me go back to a slide that can actually represent what I mean. Even within this battery pack here, typically cells are arranged and connected in series and parallel. However, there are some cases within battery packs where this particular cell might fail, which will affect the entire performance of the battery pack. So one thing that potentially I could do in the future is looking at not only how many cells fail, but where the cells fail. If this cell fails and the fluid around this cell actually doesn't change in temperature, it could actually change the performance of the cells behind it in terms of the direction of the flow. So that what you're talking about can definitely have very significant ramifications for battery modeling and can open a lot of doors. And I guess studies can be done on quantifying those types of uncertainties within your problem.
Great.
Good,
Thank
thanks.
you very much. Thank you, Matthew, and thank you all for your questions. I believe Benjamin may stop recording now since we're at the end of Matthew's session.